All right, so happy new year, happy 2023 everyone. Welcome to episode 29. So if you've been following the channel, you know I'm working on a 6809 8-bit computer system and I would like to hook up some kind of display to it, and I've made a few videos about a custom FPGA based display processor, and I've made quite a bit of progress on it, but there's still a lot to do, and the progress has been relatively slow because I don't have huge amounts of free time lately. And also, I don't know a ton about FPGAs, so there's still a lot to do on that project. So currently, I'm in the break between my fall and spring semesters, and I have a little bit of free time before the spring semester starts, maybe a week or two, and I would like to move this project forward, but I don't think working on the FPGA-based video processor is going to resolve to something that I can really make a video about. So what I'm wondering is, can I use an off-the-shelf solution to attach a display to this computer? And the obvious choice is the TI TMS9918A Video Display Processor. And what I'm wondering is, could I just get this working pretty quickly and have a display for the system? Alright, so at this point I would like to acknowledge Troy Schrapel, who made a comment on my first video about video display options suggesting the TMS9918A, and Troy is the originator of a really impressive 6502 based system that I have definitely drawn significant inspiration from, so great suggestion. I am finally going with it, so thank you, Troy. Definitely appreciate the advice. Okay, so let's think about how we could get started on using this chip. All right, so before we get too deeply into the technical electronic interfacing aspects of using the 9918A, let me talk a little bit about it just to give you some background. So this chip was used in the Texas Instruments 994A home computer. It was also used in the MSX1 computers that were quite popular in Japan and Europe. So it was a pretty widely used chip, and to this day it is quite readily available on the used market, so you can get them on eBay for about $5. So that definitely makes it a pretty attractive choice for this type of project. In terms of its features, it can display 256 by 192 pixels as its basic resolution. It can display 15 different colors. There is one color reserved as transparency because you can use this chip to overlay a picture on top of an existing video signal. It can support up to 16 kilobytes of video memory, which by default is meant to be dynamic RAM. However, it is possible to interface this chip with static RAM, as we will see. There is a text mode that can display 40 columns by 24 rows of monochrome text. There are also a couple of modes in which you can put 32 by 24 color text characters onto the screen, and sprites are also supported in this mode overlaid on top of these text characters. However, the text characters don't necessarily need to be text characters because their pixels are formed from arbitrary patterns that can be programmed into the video memory, and so really these function in some sense like bitmapped graphics mode. However, we don't have complete control over the exact color of each pixel. There are some restrictions that I think are along the lines of groups of 8 pixels can be selected among 2 different colors, but in any case it's more oriented towards displaying patterns, and so it's a little bit more like the NES graphics chip than it is a modern fully bitmapped display processor. So for output, we get 60 Hz NTSC composite out of this particular chip, and of course this was designed to be hooked up to a television or a composite monitor, so not huge resolution, but certainly something that will be reasonable for our purposes. So in thinking about how to get started on this project, I think there were 3 issues that were on my mind. One is I knew that I was going to need to use static RAM instead of dynamic RAM, and I've seen various circuits to allow this, but I don't have any direct experience with using them, so that was a question I needed to answer. I have some TMS9918A chips, but I have no way to verify that they actually work, so I need a circuit that would allow me to test them and gain some confidence that the chip I want to use actually is functional. And then finally, I need to know something about how to actually program this chip so that it will display some graphics and text on the screen. So I could have sat down with a data sheet and really tried to understand it completely and figured the stuff out on my own. However, I came across a video by Dr. Volt in which he develops an Arduino-based test circuit for this chip, and that basically ticked all of my boxes. He was using a static RAM. This was a circuit I could build on the breadboard driven by an Arduino, which would give me a good way to verify that the chip is functional, and he provides an Arduino library that shows how to program the chip, and I figured that would be a good way for me to get started in using my 6809 to program this chip. All right, so let me talk a little bit about the schematic and how the circuit works. All right, so here is Dr. Volt's circuit. So let's start by showing you what everything is. So this chip over here on the left is the Arduino. That just pretends to be an 8-bit host system. This chip here is the TMS9918A Video Display Processor. And then these 3 chips over here are all 748CT574 8-bit registers. The top one is used to latch 1 data byte so that it can be sent from the VDP to the video memory, and then the middle one and the bottom one are registers that store the row address information and the column address information, and those basically will be combined to address a particular byte of video memory. And then this chip over here on the right is just a 32K static RAM chip, and that's the actual video memory for the display. So the interface between the host system and the VDP is fairly straightforward. We have a pretty standard parallel data bus, so this allows the host system to send 8 bits of data, 1 byte of data to the VDP, and it also allows the host system to read 1 byte of data from the VDP. There are active low read and write signals that are used by the host system to indicate when it wants to read a byte from the VDP or write a byte to the VDP. The mode signal allows the CPU to indicate to the VDP whether it wants to read or write data or address information. And the reset signal is used by the host system to reset the VDP. Because the VDP was designed to use dynamic RAM as the video memory, it outputs address information in the form of a row address and a column address, and the RAS, row address strobe, and CAS, column address strobe signals indicate that address information for the row or column is available on the VDP data bus. So the way that the row address register and the column address register work is basically the same. The row address produces the low 7 bits of each address, and the column address produces the upper 7 bits of each address. So I will just talk about the row addresses. So let's say that the VDP is asserting the row address strobe. That goes through this inverter and then gets connected to the clock input of this 748CT574 register. And so basically the idea is that when the VDP wants to write data to the row address register, it lowers the RAS signal, and of course the inverted form of the RAS signal will be the opposite. And so it's on the positive edge of the clock that the register actually takes the information that's being output and then stores it in the register. And so the production of an address basically involves writing 7 bits both to the row address register and the column address register. That produces the entire 14-bit address value that is used to index into one of the memory locations in the video memory. So the most interesting part of this circuit is the support for writing data from the VDP to the video memory. So that happens when the VDP asserts this RW signal, which is active low and is asserted when the VDP wants to send a byte of data to the video memory. So that signal goes both to the output enable of this data register here and also to the write enable input of the static RAM. All right, so here's what the VDP is going to do when it wants to write a byte of data to the video memory. It will drive the RW signal low. And basically during the duration of the time that this signal is low, that is when data is being presented on the VDP's data bus corresponding to the byte that the VDP wants to store in the video memory. So what you might be wondering at this point is, why do we need this register here to store the data that is being sent from the VDP to the video memory temporarily, given that that data in theory is valid during this pulse? And so the answer is, according to the data sheet, it's really not clear that all of the data on the VDP's data bus is valid for the entirety of this pulse. And I've looked at the timing diagram, and basically the point at which this RW signal is deasserted is, on the data sheet, pretty much exactly the same point at which the data on the VDP data bus is also marked as not being valid anymore. And so the approach taken by Dr. Volt's circuit here is to use this inverter to produce the complement of this signal that is low while reading and high while writing. And so that produces a positive going clock edge that is then sent to the clock input on this register. And so basically, right at the beginning of when the write pulse begins, the data that's on the VDP data bus is latched into this register. And that means it will continue to be valid as long as necessary, and we don't have to worry about it becoming invalid before the end of this pulse. So that is the explanation for why this register is apparently necessary. All right, a couple final quick things to note. So these pins here on the VDP are the ones that allow it to read data from the static RAM. So it's not entirely clear from the schematic, but they are connected to these data pins on the static RAM. So if the CPU wants to read a byte from video memory, the data is transferred from the static RAM to these inputs of the VDP, and from there conveyed to the CPU via the data bus. And finally, our composite video signal comes out on pin 36, and then it is amplified by this transistor, and then it can be sent to our monitor or other composite display device. All right, now that we've understood the circuit, let's go ahead and build it on a breadboard. All right, in a moment I'll show you the circuit, but first let's have a quick visit with Ingo. All right, so here is our circuit, pretty much ready for testing. We have our Arduino, the TMS9918A. We have the 32K SRAM under here, kind of hard to see. I think this is a cache memory chip, probably from an old motherboard. And here's the 74 ATT 04 hex inverters that are used in the circuit, and then we have the data register, the row address register and column address registers here. So I will share two construction tips that I have found useful. So one of them is I have a printout of the schematic that I work from, and here I've made a blue check mark every time I make a connection, and then the green check marks indicate that I've used the multimeter to verify continuity to whatever other pins the connection is supposed to go to. And that way I have some reasonable confidence that the circuit that I've constructed on the breadboard is the one that is described in the schematic. The other tip is, as you can see, I am definitely not Ben Eater. I don't really try to make particularly neat breadboard circuits. You know, the point of breadboard construction is to prototype, not necessarily for finished construction. So I've made significant use of these DuPont wires for basically for all of the parallel data and address connections that are all over the place. And I've used color coding to indicate which signal in a parallel bus I am connecting. And that's actually quite helpful because it provides some visual indication of which data bits and which address bits are going where. And I actually caught at least one error in my wiring just based on seeing that the colors didn't match up. So, you know, that can be useful. Okay, so let's try this out. All right, so here is our test circuit hooked up to this LCD monitor that's from a car DVD player, but it's just a composite monitor that runs off of 12 volts. And as you can see, it's working. This is the sprites demo from Dr. Volt's demo project, which is the one that we started from. And everything basically looks great, except for there are no colors. And, I don't know exactly why we're not seeing color here. Clearly, this monitor was not necessarily designed to support output from these old computer video display chips, so I will investigate other options for displaying composite video. But certainly this is a really excellent sign, because it means that the circuit is working, the VDP is working, the SRAM is working. That's really great. Also, I have a total of 5 of these TMS9918A chips, so all 5 of them actually work in this circuit, so that's definitely nice to know. Given that they were all sourced from eBay from random sellers, you don't necessarily know that you're getting a working chip, so certainly it is nice to know that all of these are working. I was interested in the current draw. So for the circuit, it's currently drawing about 240 milliamps. So, it's a little power hungry. These things definitely do get a little hot, so I will probably put a heat sink on it at some point. But overall, I'm very pleased with this progress. So I think our next step is to try to interface this to the actual 6809 system. And, given that the Arduino is simply pretending to be an 8-bit computer, in theory it should be pretty straightforward to connect the circuit to an actual 8-bit computer. So I think that's our next step. All right, so at this point, we're ready to interface the 9918A to our 8-bit system. So I have made a more or less exact copy of Dr. Volt's schematic and added it to the overall schematic for the system. So again, I take no credit for this. This is just a copy of Dr. Volt's work. The main problem I need to solve here is that I need to adapt the active low write and active low read inputs that the 9918A has, so that they can be generated by an active low chip select and our read-write signal that are coming from the 8-bit system. So let me tell you about how I plan to do that. All right, so anytime you are going to implement some logic, it makes sense to start thinking about whether you can use exclusively NOR gates or exclusively NAND gates to solve the problem. And so here I've elected to use NAND gates. So let's think about what's going to happen if the host system wants to read a byte from the 9918A. It's going to assert the chip select, so the chip select will be 0, and the read-write line will be 1, indicating a read. So the NAND gate over here that is going to generate the active low read signal that goes to the 9918A, we want that to generate a 0, a low, and so a NAND gate is going to generate a low only when both of its inputs are high, meaning 1. So the read-write line is high, and so we need to invert the chip select. So this inverted chip select is also going to be 1, and that will produce a 0, which then comes up here to the read input, and that's how the 9918A knows that the host system wants to read a byte. All right, so in the case that the host system wants to write a byte to the 9918A, we obviously want to generate a 0, a low, for the active low write. And so that means, again, it's being generated by a NAND gate, so both of the inputs need to be high. So the chip select, of course, will be 0 when the 9918A is selected, and so that just comes here as an inversion of the chip select. And then we also need to invert the 0, the low, that's going to appear on this read-write signal because we're writing. So we use this NAND gate here as an inverter, and that produces a 1 here. And so that means that we get a 0, a low value being asserted on the active low write input of the 9918A. And so that's how it knows that the CPU wants to write a byte. All right, so here we have our test set up. So here's our 6809 system. Here is the VDP test circuit. And basically I've just taken out the Arduino and then made connections to appropriate backplane signals on the 8-bit system. And of course I've got it hooked up to our LCD display here. So in theory, I have written some code that will enable text mode on the VDP and display some text. So let's see if it works. All right, so let's put a camera on our LCD display and I will power on the circuit. So hopefully we'll see some text. And there it is. So we have successfully displayed some text in the 40x24 text mode. And at this point, our 8-bit system is indeed using the VDP to drive a display. So that's what we set out to do. So fantastic. All right, so let me talk very briefly about programming the VDP. So there are two memory mapped I/O ports that we use, and one is used if we want to transfer data to or from the video memory, and the other is used if we want to access one of the VDP's internal registers. So for now, all of the code to program the VDP is called from this initialization routine, and right now all it does is set the internal registers to appropriate initial values for text mode, clears out the video memory, loads a font into the pattern area of memory, and then adds some ASCII characters to the name table, which is basically the frame buffer, to display a message. I wrote a couple of helper routines, one to write one of the internal registers and another to set the address that is going to be accessed in the video memory, and all of these involve writes to the control port. So you'll notice I have some calls to this delay routine, and basically you must delay a bit after reading or writing one of the VDP registers because there are some timing requirements that you must adhere to in order for the reads and writes to work correctly. I haven't fully investigated exactly how long those delays should be, so for now there's just a sufficiently long delay that the code does work correctly. So the routines to clear the video memory and to load a font into video memory are quite similar in the sense that they simply write bytes repeatedly to the VDP's data port. And the internal address register in the VDP is auto-incrementing, so when you write a series of bytes to the data port, they go into sequential memory locations in the video RAM, which of course is generally what you want to do. So the clear routine just writes zeros repeatedly, and the load font routine loads font data from the program ROM in the host system and puts that into the pattern table in video memory. Finally, here is the routine that writes a string into video memory, and basically it just goes through the bytes of the string one by one, writing them to the data port until it reaches the null terminator, so pretty straightforward. So I believe what happens when you put a ASCII character in the video memory is that you're technically putting it in the name table. Each entry in the name table references an item in the pattern table, and in the 40x24 text mode, each name refers to a sequence of 8 bytes, specifying the 8 rows of pixels forming one character to be displayed on the screen. I also must acknowledge that the font that I am using was 100% copied from Dr. Volt's demo, so I appreciate him making that code available so that I could steal it and use it in my project. Finally, here's our delay routine, and it's just a bunch of NOP instructions, and it's not based on any actual understanding or analysis of the timing requirements. It was just determined experimentally to work in my test setup. I really should go back and look at the datasheet in more detail so that I fully understand what the timing requirements are. Okay, so to conclude, let's talk about what we can do next. And I think the main thing is actually at this point software support. So one of the main things is I would like to update the console routine so that the VDP can be used as the console output device. And this is actually pretty exciting because it means that we now have the possibility that the system can be used completely independently of a PC because we have our keyboard already implemented. With a display device, this now becomes a completely standalone system. Also, it would be nice to start experimenting with some of the graphics modes and maybe displaying sprites. And the other thing to do would be to actually permanently construct the VDP circuit as a card that can be plugged into the backplane, and obviously that would be a lot more reliable than having it set up as a breadboard connected to the backplane using flying wires. Alright, as always, the links to the schematics and the code are in the video description, and that's it for now, and I will see you in the next video.